Shall be so so thanks for inviting me. So today I shall tell you about a problem that has been occupying us recently, and that is the problem of displacing non-Newtonian fluids in confined geometries. I shall be talking to you today about our recent experiments on the displacement of a very, very familiar material, colloidal clay in aqueous suspension. And we will displace the colloidal clay using Newtonian fluids of different miscibility. So the colloidal clay here is an aqueous suspension. So we'll be displacing it in a Hele-Shaw cell geometry by water and oil. And I'll show you the patterns that are formed. I'll tell you how these patterns are selected and how the selection of patterns depends on the spatio-temporal growth of these patterns. So the work here was done by my PhD students, Palak, who got her degree last year, and Vaibhav, who's going to be submitting his dissertation very soon. Okay, so because I don't suppose any of us have really met before, I thought I'll just quickly tell you what our group works on. So we are called the Rio DLS Laboratory because when I joined the Raman Research Institute almost now 20 years ago, the main techniques we used to use to look at the structure dynamics and stability of soft matter were rheology and dynamic light scattering. But now we have we've really expanded our interests a lot. So there are a few research themes that I thought, I just kind of categorized our recent research into some research themes. So first is our bread and butter. That's to look at the structure dynamics and rheology of jammed suspensions, and the techniques that we use are rheology, dynamic light scattering, we do cryogenics, scanning electron microscopy, we do confocal microscopy, we do rheodielectric studies, we do rheo small angle light scattering. And some of the questions, these are just some of them that we are trying to understand, is that how do interparticle interactions influence the emergent properties of these soft glassy materials? Nowadays, we've learned how to make our own soft glassy materials, so we can also engineer the interparticle interactions between them, which is a lot of fun. We look at structure dynamics, rheology correlations in these jammed suspensions, and these dense suspensions, as they approach their glass transitions, we look at how their non-Gaussian dynamics grows. Okay, but I'm not going to tell you about this today. Neither am I going to tell you about the research theme 2, which is basically the physics of suspensions that are acted upon by external fields, such as shears or even electric fields if the soft material is charged. So for this, we use particle tracking microrheology, we do optical tweezing, we make our own viscometers, we look at how macroscopic objects fall through not through a viscous medium, but through viscoelastic media. We look at what happens to the end effects, the side of, the wall effects and so on. We look at the length scale dependent rheology of highly heterogeneous colloidal materials. For this, again, we use optical tweezers and optical tweezer based active microrheology. And like I told you, we also look at how charged materials of different shapes and sizes, mostly colloidal, and suspended in different media, how they respond to electric fields. The third is the instabilities in quasi two-dimensional geometries. This actually started very recently for us with Palak's thesis. And well, now that she's gone, we are looking at a different kind of instability, which is evaporation-induced self-assembly. So we look at coffee stains after suspension droplets dry, or we look at desiccation cracks in thin films and thin colloidal layers. But I'll be telling you today about research theme number 2. So I know I don't need to spell this out to this audience, but then let me start by telling you this anyway. Instabilities, as we all know, are driven by pressure gradients, by viscosity contrasts, interfacial tensions, and also they can be driven by the imposition of external fields. And of course, we see patterns all around us in nature. And all these patterns that form in nature, they always form to optimize some function or the other. In the case of the branches of the trees, for instance, the branching out of the trees, okay, it just means that the leaves will get more sunlight and oxygen and to perform photosynthesis. The branching morphogenesis of the human airway tract, that just delivers maximum oxygen to the cells. And of course, in the laboratory, we look at instabilities too. We love patterns. They are so beautiful to see. One of the most common instabilities, of course, is the Safman-Taylor instability, the viscous fingering instability. And on the right here, I have a picture. I have an image from the seminal paper by Safman and Taylor. So what you see here, this here is glycerol. And these protrusions that you see here, these are basically tongues of oil that are protruding into the glycerol. Okay, so it's basically a less viscous material that is invading a more viscous material under gravity. And you can see these, and you can see that the air does not really invade the glycerol as a nice homogeneous front, but it forms these tongues or fingers. So that's an instability. As I was saying that, viscous displacements have been something that we've been looking at for a very long time. But then we thought, and again, more recently, there have been lots of studies also of what happens when less viscous Newtonian liquids, they intrude into viscoelastic materials. But what we did here was we looked at what happens when a less viscous material of different miscibilities, in this case, we've used water as well as oil, they intrude into an aging non-Newtonian fluid. And the aging material that we've used here is clay. Now, what do we mean by aging? So clays do something called physical aging, which means that because clays are charged, as I'll just show you, and because the interparticle interactions keep developing with time, okay, the properties, the emergent properties of clay, they gradually and spontaneously, they develop with time. So if you just make a clay suspension and if you just observe it, you'll see that the mechanical moduli, they are building up spontaneously. So that's physical aging, right? So clay, of course, is a very, very common material. We've all seen the flow of mud slurries. Clays are also terribly useful. We use them in pottery. They have industrial uses. They have therapeutic uses. They're also used in research by some people like us who use clays it's a wonderful colloidal material to understand the jamming transition. But have you ever seen or have you ever wondered what clay looks like? This is what clay looks like under a scanning electron microscope. So it is a weak gel. Okay, so you can see the scale bar here. It's 2 microns. Okay, so what you have is a self-assembled gel assembled by the interactions between particles, between clay particles that form these very weak network structures that are held together by screened electrostatic interactions. So the two main properties of clay are the following. One is that it is a very fragile gel. It can be very, very easily ruptured because there are no physical contacts, but it is held together just by these screened electrostatic interactions. And the other very interesting property is that the gels age. That is, their structures evolve over time. So in the next few slides, I'll tell you why this aging happens. So for our study here, clays, as you know, you can have all kinds of clays. There's bentonite clay, there's kaolinite clay, but for the study here, we'll use laponite clay, which is a kind of a designer clay. It forms soft, glassy colloidal suspensions. They also age. They do exactly what other clay suspensions do, except that all the clay particles here, these all have the same size. They are monodisperse. So they are about 25 nanometer across and 1 nanometer wide. Okay, and here's it has a layered structure. Clay is an inorganic molecule, macromolecule, and so as you can see, it's a disk, and on the surface of the disk there are all these sodium ions. The green balls here are basically cartoons for sodium ions. And when you buy clay from, say, Sigma Aldrich, when you buy laponite, this is what they look like. They're these clumpy materials, and they're not individual clay particles, but they form stacks like this. So this is a kind of an artist's impression of the aggregated particle stacks that clays form. And when you disperse these in water, the aggregated particle stacks, they break up into individual particle stacks. Now, remember, in the interlayer gallery here, you have sodium ions, right? So these sodium ions, once you put this stack in water, there is an osmotic pressure gradient between the bulk water and the and the interlayer gallery. So this results in swelling of the layer, and the sodium ions, they try to reach out into the bulk medium. So there is this swelling, and as the charge distributions continue to change in suspension, and the clays in the tectoids, these one-dimensional stacks, they continue to repel. Okay, they continue to repel because of screened electrostatic repulsion. And the moment the screened electrostatic repulsion, it exceeds the van der Waals interaction between the two particles in the tectoid, the clay stack starts breaking up. This process is called exfoliation. And because of the combined effect of this exfoliation and before that the swelling, if you look at a clay particle in a rheometer, you're going to see, I mean, if the quantity, if the content of clay is high enough, you're going to see that the elasticity and indeed the viscoelasticity of the material of the suspension continues to build up over time for hours. And here and what I didn't tell you is that if the pH of the medium, if the aqueous solution, if the aqueous medium in which your clay particles are suspended, if that is less than 11, in that case, there are these side groups which are magnesium, right? So the magnesia here, that gets hydrated. Therefore, you end up with these particles which have negatively charged faces and they have positively charged sides. So when you have many such particles together in water, they can aggregate. So these are negative faces that attach to the positive rims, and you can form these house of cards structures. And as these house of cards structures develop, as the charge distribution in the suspension changes, they eventually span the whole system. And you can actually see in a matter of hours that your clay suspension goes from a liquid to a solid-like state completely spontaneously. And indeed, we had made these measurements many, many years ago. So here I'll define this quantity TW, which we call the aging time. This is the time since preparation. So you just prepare the suspension and then you start measuring here. What we've done here is we've measured the sodium ion content in the bulk water medium using a sodium ion sensor. You can also do this with conductivity, but then for that you have to assume that DLVO works, which may not be entirely true. But if you just measure the sodium ion content in water with the age of the suspension, so you're not really disturbing the suspension, you're just letting it evolve, and you're measuring the sodium ion content in millimolar per liter. And sure enough, you can see that over here we have measured for 30 hours. I beg your pardon. You can see that the sodium ions continue to build up. Okay. And what does a clay suspension look like? What does aging look like in the laboratory? So when we first make a clay suspension, we just take the clay powder and we disperse it in water. We also mix it up a bit and we try to break up as many of these stacks as possible. But then immediately after preparation, and it's in a vial, it is nicely sealed to minimize evaporation. You can see that, you can see the meniscus flows. Okay. So basically, if you look at the viscosity of this material, it's about 10 times more viscous than water, maybe 10 millipascal second at room temperature. Okay. And you can see it flows, but you just make sure that this is nicely wrapped in paraffin. There's been, very little evaporation and nobody has come and fooled around with the system. Come back after 24 hours and your material here has become a solid. So here you can see one of us taking the same vial, turning it over, and you can see that the sample, it can actually support its own weight. So what you have got here is a transition from a liquid-like to a solid-like state with time. Okay, and it's a spontaneous transition. So this is physical aging. This is happening because of the development of interactions in the suspension. Just like in biological aging, we age and we get wrinkles, our hair turns gray for us. Okay, so similarly here the interactions evolve and you can actually go from a liquid to a solid. And in a measurement that we did a little while ago, and I'll tell you more from this paper. So we've measured here the elastic and the viscous moduli versus the aging time, okay, TW, that I told you about earlier. So these are measurements that are made in what we hope is the linear regime. So very, very small peak-to-peak amplitudes of oscillation and very small frequencies. And what you see here, and I should tell you here that the hollow symbols here are the viscous moduli. The solid symbols here are the elastic moduli. And you can see that initially, for a very, very fresh sample, you can see that the viscous modulus is higher than the elastic modulus. So the suspension flows, which is what I showed here. And this is possibly because you still have some clay particles that are free to diffuse around. Clay particles or maybe even some tectoids. But then as you just wait and you let your system spontaneously age as the interparticle interactions evolve, you can see that the elasticity overtakes the viscosity. And eventually, if you wait for about 10 hours or so, then the system becomes elastic. So here it is more elastic than viscous, which is what we saw here visually. And this is because of the formation of the house of cards structure. So you're going from a liquid to a solid. You can see that the solid continues to evolve, and that is because of the gradual restructuring of this gel that happens. So initially the gel spans the whole system. It becomes rigid as it starts going from one wall of your container to the other. And after that, it continues to evolve. Okay, and that is why you can see that the elasticity continues to grow. And so this is aging, this is physical aging. Now, clay being viscoelastic, there is another thing that it does, which is it also shear thins. So here I have three different clays, which I've aged to three different durations, and then I just apply a rotational shear rate, and you can see that as the shear rate increases, you can see that the viscosity decreases by orders of magnitude. So what we are going to do in our Hele-Shaw cell experiments is that we are going to exploit this time-dependent and shear rate-dependent rheology of the outer clay suspension, and we are going to see what kind of patterns we get when this clay in a very, very confined geometry is invaded by water or oil. Okay, so this is the very familiar geometry that we've used. We've used a Hele-Shaw cell. So we've used these round plates, glass plates, about 30 centimeters in diameter. Each glass plate is about 1 centimeter wide. And the two glass plates are really close together, but they are separated by a gap of 170 microns, which we obtain by putting some Teflon spacers. So this is the geometry. And initially what we do is the purple fluid outside, which has been displaced by the red fluid here. So this is our interface, right, that we've created. So initially, this purple fluid would be our clay suspension. So initially, we use a syringe pump to pump in our purple fluid. And then after that, we pump in, we wait for some time. So we want the clay to age. So we first fill the purple fluid here, the displaced fluid or the clay. We wait for predetermined amounts of time, and then we inject the second fluid. Okay, in this case, the red fluid, which is either oil or water, in separate experiments. And then we look at the growth of the interface. In most cases, the interfacial growth is unstable, and that is what we follow with this DSLR camera from the bottom. And so that our data looks good, we illuminate it from the top. And just to remind you, so in this case, the displaced fluid is our soft, glassy laponite suspension, and which is non-Newtonian. And not only is it non-Newtonian, it also ages. Its properties evolve with time. Okay, and the displacing fluid, which is the red fluid here that we injected the second time, is either water or mineral oil. And when you look at the viscosity, so this is for water and this is for mineral oil, when you look at it under rotational shears, unlike for the laponite suspension, you can see that the viscosity of the water and the mineral oil, both Newtonian liquids, they do not change with shear rate, but also do note that the mineral oil viscosity is a lot higher. I have really, I have kind of labeled the immiscible displacement or the data with invading oil as red, because we've used oil red O as a dye, so that there's a good contrast at the interface. So the oil has been dyed, the mineral oil has been dyed with oil red O. These are the red points here. And the water, when it invades the clay, the water has been dyed with rhodamine B. Okay, so here's our data. So what this gray thing that you see here, this is the clay in the Hele-Shaw cell, but you're watching it, you're seeing it from the bottom because that's where the camera is. So I'm going to first show you what happens when dyed water invades the clay. And this is what I'm going to call miscible displacement. And so let me just play this. So the water is going to be injected at a constant flow rate of 5 ml per minute. And this is what we see. Okay, we see this very dense viscous pattern that develops. Now, if you look at it very, very closely, you'll see that, there are these narrow, thin branches that propagate, but they also keep, merging with each other. The branches, because remember this, the age of the clay here, it is very, very low. It is pretty much freshly prepared. So, because it is freshly prepared, it is not very viscoelastic. It is rather viscous. So the viscosity mismatch is not very high between the water and the outside clay, the clay suspension. So what you end up with is this, what we call a dense viscous pattern. Okay, and these have lots of, there is no clear, there's no well-defined boundary, and you have these, these branches keep interconnecting. They keep interconnecting because of the low viscosity of the outer clay here. And you form these little pools of clay inside. But you can see, I just want you to notice this, because in the next plot, what I'll show you in the next image, what we've done is we've filled the clay in the Hele-Shaw cell and we've allowed it to age for 3 hours. So the clay here is a little more elastic than it was here. Okay, and now let's just get the dyed water to invade, and this is what you see. You see a very different pattern. What you see is a dendritic pattern. So dendritic pattern with lots of side branches. In the dense viscous pattern, I know it was difficult to really look at these features in this very quick video. There was a lot of tip splitting, but there was very little side branching. But the moment the elasticity of the phase outside increased, you see a lot more side branching. But much of the side branching actually happens towards the beginning of the growth of the interface. But here, unlike here, you can see very, very clearly defined interfaces. Okay, and one word about side branching. The reason why that happens is the fluid outside the clay, that is shear thinning. So as the water that is propagating into the clay at rather high velocities, it shear thins the clay at the propagation front, and the combined effect of that shear thinning, that results in the finger propagating faster. But remember, the driving pressures on the water, those are also very high. So that tends to make the branch. So here's what we got when, you had intermediate elasticity. So here we've loaded the sample and we've allowed it to age till 24 hours, 1 day. So this outside clay suspension that you see, this is extremely elastic. So now we are going to inject the water, and this is what you see. You see cracks. This is exactly what I'd get if I just took a stone and I threw it on the glass, right? So now remember, the material outside is very elastic. So when you invade this very elastic material, this gel-like clay suspension outside with the water, you can see initially there are these primary branches that form, just like it does in any crack propagation. And after some time, you have these narrow perpendicular offshoots that develop. See how narrow these tips are, right? And this is happening because the water is invading. As the water is invading the clay, it is basically yielding the underlying clay networks. Okay, so there is an yielding going on, there is a rearrangement going on of this very, very, so there's a lot of, release of elastic stresses, and that is why you form, very, very, crack propagation patterns like this, which we call viscoelastic fractures. So very similar cracks were also seen when aqueous foam was invaded with water. And foam, as you know, is an yield stress material. Now we've repeated these experiments at many other different ages of the clay. And you can see that as the clay age increases from here and then all the way to here, so elasticity is increasing with time. You can see how the patterns gradually transform from these very dense viscous patterns through these dendritic patterns, and then ultimately we have these viscoelastic fractures. Now, I've been telling you about miscible displacement. What happens when aqueous clay suspensions of different ages and hence different elasticities are invaded by water, which is miscible in clay. Now, what happens when you invade the clay not with water but with oil? And oil, as it doesn't wet clay, right? So there is this interfacial tension, which should have a stabilizing effect. So let me show you what happens. So here again, we are going to use laponite, the clay suspension at 1 hour and 24 hours. I'm just showing you the two ends of the spectrum in clay age. And I'm going to invade clay here and at the same flow rate as I did the water. And this is what you see. So initially, because of the stabilizing effect of surface tension, you have this very uniform growth of the of the front of the interfacial. You have a very stable interfacial growth. And now you can see as shear thinning takes over, you can see some undulations growing. And eventually, as you can already see that this is way slower than what we saw with the uh, when you were invading the clay with water. So I'm going to speed it up. And this is what eventually the pattern looks like. It reminded us of a flower. So we call this a flower pattern. Okay, so this is when the clay was shear thinning. It was still much more viscous than it was elastic. But remember, the mineral oil had a lower viscosity contrast with water. And along with that, you have the stabilizing effect of surface tension. So you end up with a pattern where the coverage is much, much better than what you got for the miscible displacement experiments. Now here, we've aged the clay up to 24 hours, and then we are going to intrude the clay. Then the oil is going to invade the clay, and this is what you see. You see what we call jagged patterns. Okay, so again, like I told you, these jagged patterns, as you can see, it is not as you don't get the kind of the stable growth that you initially got. And that is because of the elastic instability, which is present from the very beginning because of the very high elasticity of the surrounding clay medium. But this is also much slower than the miscible displacement experiments. So I'm going to speed it up a bit. And this is what our final pattern looks like at the time at which we analyzed our data. Okay, and again, here we have more data. So clay of different ages that are being invaded by oil. And you can see that as the elasticity of the clay increases because the age increases, you go from this more stable pattern to these jagged patterns. So now let us just do some analysis of the data. So here we have the U bar here is the speed of the longest fingertip that we have measured using videography. And here you see that as the age of the clay increases for miscible displacements, you see that the speed of the fingertip really becomes faster as you go from the dense viscous pattern to the viscoelastic fingering pattern. But then when the interfacial tension was not zero, when you use mineral oil, you can see that firstly, you can see that the fingertip speeds are extremely slow when compared to what you got for the miscible displacements. But then they also do not really change with the age of the clay suspension outside. So what we've done here is we've calculated a shear rate of invasion here. So we have assumed non-slip boundary conditions and a parabolic profile of the invading fluid in the gap. And we have used this approximation. So B is the thickness of the gap. And with that, we see that the miscible fluid, the water, invades the clay at shear rates that are between 34 to very big shear rates, like 550 per second. But for the clay, the shear rates are much, much lower. And this is, of course, because of surface tension. Now, we've done some analysis, but I think to save time, I'm not going to be able to tell you everything because of all the technical difficulties. So what we've done here is we have quantified the morphologies of the patterns by calculating, by proposing a parameter which we call the areal ratio. So the areal ratio is basically the coverage area of the pattern divided by the area of the smallest circle that encloses the whole pattern when the longest finger has reached a particular radius r. In this case, we've just arbitrarily defined a radius r of capital R of 7 centimeters. We've also looked at this annulus here between the radii small r and big R, and we've calculated two other parameters. One is the average width of the branches for the branches in this annulus, and also the average frequency of the branches. How many branches do you have over this whole annulus? Okay. And here are the patterns that we formed. This is with surface tension 0. This is with surface tension not equal to 0. This is the development of the patterns as the age of the clay increases. And we've calculated the areal ratio, okay, this particular ratio for all the materials, for all the experiments that we've done. And you can see that the black points here are for the miscible displacements. And as you can see, the coverage of the miscible displacement patterns are much, much smaller than the immiscible displacement patterns. So sure enough, the areal ratios are much lower for the miscible displacements than they are for the immiscible displacements. Okay, so now we've done another slightly, a related experiment, but we thought, see, so far all the data I've been showing you, they've been taken at a constant, all the data has been taken at a constant flow rate of the injected fluid, that is the oil or the water, but we've changed the age of the clay suspension. But what we've done here is that we've increased here we have changed the flow rate, but we have kept the age fixed. At the age of the displaced clay suspension, we've kept fixed at 24 hours. And obviously, as you increase the flow rate Q, what you're doing is you are just shear thinning the medium outside. So as you increase the flow rate, so Q here is the flow rate, going all the way from 1 ml per minute all the way up to 50 ml per minute. So far I was showing you data here at different ages. Okay, so as you change the shear rate, on the clay suspension by increasing the flow velocity, the volumetric flow of the Newtonian liquids, you can see that you get the same sequence of patterns, but in the reverse direction, right? Because as you increase the flow rate, the viscosity of the clay, the elasticity decreases. You are shear thinning the outer clay suspension at very high flow rates, okay, by breaking up all the structures because you're imposing very, very large velocities on the outer clay suspension. Okay, so we've done a similar kind of an analysis where again we've looked at the coverage of these patterns as you change the flow rates. So here is here are the patterns that we got for different flow rates and also for the different miscibility conditions. And we've plotted here the coverage ratio as I defined it earlier. We've also looked at the branch frequency and the branch widths, but I thought I'm not going to talk about it because it's already, it's been 40 minutes already. So, and what we see here again is that, well, you get exactly what you got when the flow rate was constant, but when the age of the outer clay suspension was increasing, but you get it in reverse. Okay. So then what we've done here is we've calculated the viscosity ratios because, we just wanted to see what the contribution of the viscous instability was. So we've calculated the viscosity ratios for all we know, of course, the viscosity of the water and the oil, but because the viscosity of the outer clay, that depends on the shear rate, we've calculated the viscosity of the clay suspension at that age, at that particular shear rate in a rheometer. And we have plotted here the viscosity ratio between the inner fluid, that is the Newtonian fluid, and the outer fluid, that is clay, at different ages, and also when it is being inverted at different flow rates. And this is all our data. And you can see that as you increase, so here I've just plotted it versus the injection velocity of the Newtonian fluid, you can see that they increase. So as you're increasing the injection velocity, the viscosity ratio between the viscosity contrast between the outer and the inner fluid, it becomes smaller and smaller, and that suppresses the viscous instability, which is in agreement with all the data that I've shown you so far. So just to remind you, so with time, these were the morphologies that evolved. Okay, all this is with water and all this is with oil. Now, the red ones, of course, are the data points that we got for oil, and you can see that the viscosity ratios are much more for them, and hence the stabilization. This is just, we just quantified it. Now I want you to see this purple pattern. So the fact that you can change the miscibility, you can change the age, you can change the age of the material, you can change the flow rate, and you can actually, you seem to be able to control the pattern, the emergent pattern that forms, right? So we thought, why not let us try to form a completely stable pattern? And this is the purple data point here. And this is what we got. So this is for a very low age of the clay here, and at a very, very high flow rate of the injecting oil, of the oil that we've injected here, the red fluid. As you can see, we've watched it for a very long time. We have a beautifully uniform front that propagated. So that is this point, which, as you can see, has a very high viscosity ratio. So what we are doing is we are suppressing the viscous instabilities here. Now here what we've done is the area coverage ratio that we had calculated of all the patterns, we have plotted it versus for all the samples we've done, regardless of miscibility conditions, regardless of the flow rates, regardless of the age, we have plotted it versus the frequency of the fingers and the width of the fingers as we had calculated in that little annulus at the border of the fully developed pattern morphology. And you can see that they are all very nicely linearly correlated. So we thought, let us try to separate them all on a phase diagram. So we made this three-dimensional phase diagram spanning these axes. So one was the age of the suspension, the clay suspension, the flow rate of the invading fluid, which is the water or the oil. In this case, we have plotted the data for everything. And here the bottom plane corresponds to the miscible displacement and the top plane corresponds to the immiscible displacement, and the color bar that you see here, these are the numbers that you get when you plot when you estimate the logarithm of the areal ratios of all these all the data that we've taken in our experiments. And you can see that, well, the birds of the same feather, they flock together. You can see that the colors are kind of concentrated. So this is because we are able to control the patterns by controlling these control parameters here. So our control parameters here are the age of the clay suspension that we are displacing, the displacing fluid injection velocity, which is something that we can control by controlling these, and of course also the interfacial tension. We can control the patterns that form even when the fluid pair is the same. In this case, the fluid pair is either clay and water or it is clay and oil. So then, just to see how these patterns were being selected, we looked at the growth of these spatio-temporal patterns to see if by looking at the growth of the spatio-temporal patterns, we can come to some conclusion about the final pattern morphologies that were being selected. So here you see this color scheme. The colors basically represent, they have a one-to-one mapping with the propagation time of the pattern. So blue means the pattern very early on, and the redder it gets, the more developed the pattern is. So for the dense viscous pattern, you can see the tip splitting that is happening here. And what we've plotted here is the areal ratio versus the normalized time for the fully developed pattern to grow. So that is these are the blue data points here. That's the coverage ratio. And this is the speed of the longest finger. And I'm not going to go into the areal ratio because there's not a lot of time. But what I want you to see is that as time progresses, what you achieve is a regime of steady growth. So look at the brown points here. You see that at longer times, you have steady growth. So the pattern is growing in a steady way, right? And the same for the dendritic pattern. So here we have the longest finger propagating, that's the velocity. And you can see even here eventually you have steady growth of the pattern. But look at the viscoelastic fracture here and look at the velocity, the speed at which the fracture propagates. So there is no steady regime here. So initially you have a primary crack. When the primary cracks form, you can see that the velocities, the speed of the fingertip goes up. And then after that, once the side branches start being shed, after that, that kind of limits the growth of the pattern, okay? But then you never see any steady growth, okay? Suddenly, the propagation of pattern, the propagation of the fingers become really, really slow. Now, this is for the immiscible displacements. So this is when you are invading the oil, okay, into the clay. This is when the clay was fresh, and this was when the clay was highly aged. You can see the flower pattern and the jagged patterns that formed. So if you look at the speed of the fingertip here, you can see that for the flower pattern, for the immiscible displacement, again, we get a very stable growth. We get a steady growth, and we get the steady growth pretty early on, and that is because of the stabilizing effect of the surface tension. But for the jagged pattern, when you invaded the highly elastic clay with oil, okay, so then you see this waviness in the velocity, and that is because this intermittent dynamics of at the interface, they arise because of the the breaking up of structures. Okay, the oil has to break up structures in its path, and as a result of that, you see this kind of waviness. And here again, we just thought, we just kind of segregate all the patterns based on the velocity of the fingertip. So what you see here are the miscible displacement patterns. What you see here are the immiscible displacement patterns. And sure enough, the velocities, the speeds of propagation of the longest finger, that is very, very different depending on the time and shear rate dependent rheology of the outer viscoelastic clay suspension, and of course the miscibility of the fluid pair and the flow rate of the displacing fluid. Okay, so what I want to, the take home message here is that by changing the suspension age and the displacing fluid flow rate, we have been able to actually use these control parameters to tune the growth of unstable interfaces and for the selection of patterns when clay, viscoelastic aging clay, is invaded by oil or by water in separate experiments. So the references here, so the two parts, the fully developed morphology data that I showed you and the temporal data that I rushed through, these were from these two papers. And recently, Vaibhav and I, we also wrote this invited feature article for the Europhysics letters on intrusion of Newtonian liquids into viscoelastic materials. So thank you very much for your attention. So this is our laboratory. These are the group members from a few months ago. So we do a lot of popular outreach. So here what you see, okay, so this is a lifting Hele-Shaw experiment that we've done for school, that we had done for school kids. So these are nothing but two plastic plates, and in it we had different paints. And then, you just lift the Hele-Shaw and the paints spread, okay, they spread out, the air rushes in, you get these gorgeous patterns. And well, it's fun looking at patterns. And thank you for your attention.